Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We have our lighting to the point where it's actually starting to be kind of feasible to see how this is going to ship, which is kind of cool. Because whenever you start down a path of something like global illumination, you kind of know that you're in for a little bit of hurt because no one's ever really shipped a complete lighting solution. That's kind of the be-all and end-all where we just go, this is how you do it, and you're done. It's always kind of a little bit of a hack, and actually, I shouldn't say a little bit, a lot of a hack. And so you always kind of have to come up with something that's good enough for your purposes and that runs fast enough and blah, 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 right? And we're sort of there, I think. We just have to address a couple things that we sort of, we have to figure out how we're going to tackle. And specifically, I think at this point, the really big one that we have to tackle is going to be how do we keep from having our Monte Carlo sampling, which is what we're doing at the moment. How do we keep from having that flicker too much frame to frame to be useful? So let's talk a little bit about that. This is day 418, so use day 417 source code if you are trying to follow along at home. And I'll show you what I am talking about in terms of what we need to modify here. Okay. So if we take a look at what the game looks like at the moment, with our sort of test lighting running, surprisingly in real time, which I wasn't expecting it to because we haven't moved it to the GPU yet, but somehow it is. You can kind of see as I move the light source around, we actually get pretty much what I wanted for a lighting solution. The problem is just that it flickers. Now, why does it flicker? Well, the reason it flickers is because we're using random sampling to determine what the lighting should be. So the question is, why are we using random sampling? Why does it cause a flicker? And how do we fix it? But that's really where we're at now because most of what I wanted from a global lighting solution is actually happening now. And so I'm pretty happy with where we're at. We just need to address a couple things. So there's two things I want to address. One is that flicker. The other is the skylight part of things, which we also haven't addressed yet. So we could talk about that a little bit. As well. But let's just go over where we're at because we're starting to get to a good place. And we need to start to talk about how we wrap it up and get to a thing that we're just like, okay, this is our lighting for the game and we're happy with it. We're okay with, you know, its limitations or whatever. Its downsides we've accepted and we have gotten it to the point where we're happy with it for the game. So let's talk about Flickr. Okay, so what does Monte Carlo mean anyway? We kind of talked about this before, but I'll just say it again because it's relevant. We haven't talked about it in a while. So Monte Carlo just pretty much means random, right? It also means stochastic, which is another way of saying random. And these terms have slightly different connotations potentially, but in general you can kind of think of them in the same broad category, which is to say that there are schemes which use unpredictable input, some kind of a random series, or pseudo-random series in this case, to arrive at a solution to a problem that would probably be impossible to do otherwise, right? And that's the key thing to remember, is that you're not doing random stuff because you want to, you're doing random stuff because you have to. Now, what do I mean by this? Well, let's think about the lighting equations. We've talked to them a bunch of times. When we're talking about the lighting equation, fundamentally what we're talking about is that for every point on every surface that we render, there is a whole hemisphere of information, right? A whole hemisphere of incoming light that we need to capture. And that hemisphere of incoming light, every piece of light that could be coming in from any angle would contribute to the final result. That's how real lighting works in the real world, right? A real surface takes lighting in from everywhere and radiates light out to everywhere. And it's just a different amounts of each, and what those amounts are is what determines what the surface ends up looking like, along with the properties, the microscopic properties of the surface itself, of course. That is just a tremendously huge amount of information. It's in fact an infinite amount of information if you think about it, because it's a continuous thing. There's no discrete pieces. It's not just 5 angles or 100 angles or 1,000,000 angles. It's an infinite number of angles we're talking about there, right? So the question is, how do you take something that's so infinite and vast and has so much to do with it? How do you come up with an answer, right? And so Monte Carlo schemes are one way that we have come up with, and a very common way, perhaps the only real way for certain problems that are so vast, at arriving at a solution to these problems. And what we basically do when we talk about this is we say, look, it's highly unlikely that any function really depends on an infinite number of inputs in terms of what we can perceive. What we perceive about the result of that function probably depends on a lot less than that, right? Because let's say there's a relatively uniform amount of light coming in and a relatively uniform amount of light going out. Well, then if we just sample a few places, we'll sort of capture the general idea behind the lighting, and we'll get something that's fairly close to the result, right? So the main idea behind Monte Carlo is, look, chances are there's not so much dependent on these situations. Chances are there's only a certain amount of information that's really important here, and if we randomly look, and perhaps I can also say that there's a concept of importance we can talk about in a second. If we randomly look, or better yet, look with a sort of bias towards what we think will be the most important parts of this function, we can probably arrive at an answer that's just based on sampling random parts of the input and seeing what they say. Now you can understand why this might work. Let's suppose we have a very simple concept here, right? Let's suppose that I have a rectangle. Here's my rectangle. Okay? Now let's say we don't know it's a rectangle. We have no idea yet that it's a rectangle. And the only tool that we have is the ability to start somewhere on the x-axis, right? And shoot upwards. And it'll tell us where we hit, right? So very similar to ray tracing, right? I'm talking about basically the same thing we're doing with light, where we ray trace the surface and see what's going on. Same thing, but we're just talking about finding the part of the function up here. So no one told us it's a rectangle. We don't know that, right? But this is what it looks like. All right, so how would we do this? Well, obviously it's impossible to do an infinite number of probes and scan out exactly this shape, right? But instead what we could do is we could say, well, all right, let's say that we wanted to determine the area of this rectangle. So the goal is area of rectangle. Kind of like the goal with lighting is to integrate how much light is coming in, right? We want to know how much surface this rectangle has. And we can start anywhere here and we can cast up to the top, right? Well, if we were to just do a regular sampling, right? So we just do a sampling that kind of goes regularly along it, right? Then what we would get is we would get some number of these would hit the top and some number of these would miss entirely, right? Those out here. So what we would see if we did a regular sampling, even, right? We just do a regular amount each time, and we say we're going to take, 16 samples, and we just do a regular spacing each time. We would find that some number of them, let's say, 12 of them, if this is the height of the rectangle, 12 of them come back hitting H, and the other four of other four of them come back hitting 0. They don't hit anything, right? And I shouldn't say 0, infinity. Right? They don't hit anything. They go forever, right? So then what we could estimate about that, right, is that whatever the area is that we shot along, right, however much this area is that we shot along, this would be, let's say, our width, right? Or I should say our sample width. Maybe we'll call this our sample width, right? However long we shot along, we could estimate now that around 12/16 of it, right? 12/16 of the sample width is probably roughly the width of the rectangle. We don't know, but that's how many hit, right? And similarly, we would know, well, the height appears to be on average H, because that's what we tended to hit. And we didn't hit any on these, so we don't count those. We just know that those probably weren't in the shape, right? Does that make sense? So this is a regular sampling. And if you imagine switching to a random sampling, you'd get roughly the same results, right? Let's say we just randomly shot. Well, we'd get basically the same results of this thing. We would get proportional to this sample width. The number of shots we took would fall roughly in the ratio of the sample width to the actual width. That's how many would hit. And they would all come back as H, right? So for a regular shape, a regular sampling would work, and so would a random sampling, right? So would a Monte Carlo or random sampling. Now let's say I want to do a shape that's different. Let's say I want to do a shape that's like this, right? So now I want to again take the same process and I want to estimate. What happens if I do a regular sampling? Well, I might get very unlucky. Maybe I pick a random sampling or a regular sampling that happens to be pretty close to this frequency and my random and my periodic sampling happen to be pretty close, right? So I pick here and I get that, and then I'm here, right? And I'm like doot 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 doot, right? Like so. And what you can see with something like this, and you could imagine, let's say I do, in the real worst case, I could get really unlucky and pick something that only hit right about the peak, right, or something, right? With a periodic sampling, any signal that happens to also be periodic is going to have exactly this problem, where you're drastically over or underestimating the actual area of this shape because I'm hitting the same rough place in the periodic signal, right? Now, contrast that with a random sample, which is just going to be like anywhere, right? Who knows where? That was a really bad random sample. And those random samples will not have this problem. It's almost impossible for a random series to accidentally hit common, features at any kind of period, right? In fact, the more random the sampling and the more samples you take, the less likely this is to happen. Whereas with a periodic sampling, you can always fall into that trap if the thing you're sampling has periodicity. The only chance a random sample has for doing that is if the sequence, the thing itself that you're sampling, is also completely random, and in that case, it wouldn't matter how you sampled it. You're always going to get completely random results, right? It'd be pretty hard to do anything else there. So randomness actually has a benefit that makes it likely to capture features, no matter what the underlying thing is, that any kind of a how should I put it? Any kind of a uniform sampling scheme can easily fall prey to structures in the data that you happen to line up poorly with in order to sample, right? So that's where this Monte Carlo concept comes from, is it comes from the fact that, well, look, if we're talking about something that we just can't uniformly sample in any kind of dense enough way to know that we've captured all the information, let's just throw randomness at it, and then we're at least unlikely to fall into any kind of gullies or hills that would bias us towards having a drastically high or drastically low answer. So you're using the randomness of the sampling to try and prevent systemic sampling errors from occurring. Okay? But this therefore has a downside. And the downside is that if you are sampling randomly, signals that have very specific small features that are important will get missed. Now, it's worth noting that uniform sampling probably would have missed them as well. So it's not necessarily a downside of Monte Carlo sampling versus uniform sampling, but it is the case that this can happen. For example, either scheme, let's say it looks like this, right? Now, most of my samples in the uniform case or the random case are very unlikely to be around this peak. But this peak might be very important to the function because maybe it goes really high, right? So it's a very powerful part of the signal that we're looking for. And it's very, very powerful, but it's very narrow. So neither will hit it. Neither will correctly estimate its importance, right? So this is where importance sampling comes in. Importance sampling is basically the idea that, well, we can take Monte Carlo sampling because we know that's going to be good at just generally getting a sense of the signal without biasing us towards any particular part of it or any particular pattern in it. But what we can do is concentrate our samples towards areas which we suspect will be most influential, right? And what that means in the context of what we're doing, so lighting, for example, the same things I'm talking about here are true in lighting. Let's suppose you look at the lighting of a surface, right? And that surface happens to be diffuse, okay? So all the light that's coming in from this surface, let's say it's skylight on a diffuse surface, so tons of light coming in from every angle, tons of light radiating from every angle. Any scheme will work well here. A uniform sampling scheme or a Monte Carlo scheme will both be fine because any samples you take will be right. The light is uniform, the bounce is uniform, right? So this is easy. Any sample will be correct. So no matter what you do, you're going to be okay. Now let's talk about a surface that has more specular, right? So yes, light might be coming in from everywhere, okay? But it's very biased as to how it puts that light out, right? So it's like, okay, you know, if the light comes in from here, it's going to come out this direction. If the light comes in from here, it's going to come out this direction, so on, right? Again, easy. Why? Because since the light is coming in uniformly from everywhere, it scatters uniformly to everywhere, even though it tends to be highly specular, right? Does that make sense? All right. Now let's move on to the harder cases. Now let's say we have light coming in from generally one direction, right? And we have a specular surface, so it tends to go out in one direction, right? The band, one direction. Well, now what we know is any samples of incoming lighting we take from out here are probably going to be somewhat wrong, right? Because a lot of these samples are going to say there's no light coming in, right? And so we're not getting any information from them. We want to concentrate our samples towards where the light is coming in because that's how we're going to find actual information we can use. Similarly, anyone sampling this surface to see what it's shining out, if they're sampling from here or here or here, they're going to get not much. But if they sample from here or here or here, they're going to get light, right? Because the light's coming in here and coming out here, right? So if you have information about how a surface bounces or information about where the light's coming from, you can see how you might be able to construct sampling schemes that concentrate their samples in particular areas. Now, this ends up being true in sort of a general case for surfaces in a particular way, which is because of the cosine term. So any surface, right, oftentimes has that property, the cosine theta property that we talked about before, which is that when, if you imagine a shaft of light coming in, like so, we've talked about this before, right? The steeper the shaft of light comes in, falling on the same area of a patch, right? The size of the shaft of light that can fall on that patch, right, is much wider if it's coming in this way than if it's going out that way, where it's much narrower, right? So the amount of light transferred from oblique, from angles that are very sharp to the normal is much less than the amount of light that can be transferred when it's facing dead on. So we already know that this cosine term, which we've applied many times before, right? We usually do the cosine of the angle attenuates the light source, right? Well, another thing we could do there is say, well, all right, if we're going to attenuate the light by cosine theta, what if we just sample the light in a way that skews towards upwards? So take very few samples out to the side where the attenuation is high, and take a lot more samples up here where we know the light comes in strongly, right? That's an example of importance sampling, right? It's saying how important do we think this will be to the result of the equation, right? We know the equation is like, the incident light, right? So we have the incoming light times cosine theta equals the outgoing light, right? I should maybe just write this out. Incoming times cosine theta. So we know that the equation is going to look something like this, where the incoming light is multiplied by cosine theta. We know that cosine theta of 0, right? If the angle between the normal and the incident light is 0, we know that this is going to be 1. So we're going to get all the incoming light. If the cosine between the incoming angle what am I trying to say? If we know that the cosine between the incoming angle of the light and the normal of the surface, on the other hand, was 90 degrees, right? Or pi over 4, right? I'm sorry, pi over 2. If we know the incoming angle was 90 degrees, I almost did tau there. Did you see what I did? I wrote the pi over 4 because I'm used to tau. If it was tau, let's say, over 4, but I'll stick with the radians. Pi over 2, or I should say standard notation for radians. So if the cosine of the angle was 90 degrees instead of 0 degrees, right? Then we know that that's going to be 0, which means that none of the incoming light will go into outgoing. Okay? So we know right here that we can bias our sampling because we're not going to get any incoming light from this. So we know right here that we could bias our sampling for a lot of surfaces that have this property, which is almost all surfaces, right? In the way that we're simulating them right now. There are things about glancing angle light that's there. Most surfaces also have an interesting property, which is that if the light angle is directly glancing off the surface, it does bounce quite significantly. This is how you get rim lighting. We won't quite talk about that right now because we're talking about diffuse light transfer, which is kind of a separate thing. But point being, when we're doing a reflectance function, you might see some things that are a little different than this. But we'll cover that a little later. Point being, we know that for our diffuse light bouncing around, typically speaking, we have this property that as we get to a glancing angle, as we come down further and further and further, we're reflecting less and less of that light out to everyone. So we can sort of say, well, sampling where we're going to check, we can easily say that we want to bias towards checking in the cone that's like highly above us rather than the cone that's to the side or anywhere in that sort of side angle. So that's an example of how you can bend the importance of the sampling, to go where you need it to go to improve the quality of your result, right? Okay, so I just wanted to get that basic idea out there for everyone so they understand roughly what's going on here. So what we're doing right now is basically pure Monte Carlo, more or less, right? So what's happening right now is just pure randomness. Now, it's not quite purely random because our sample hemisphere function is not quite random, right? If you look at the render group, you can see the way we do this is we normalize a random cube, essentially, which means that our hemispherical coverage is not quite random, but it's close, right? So it's basically, it's pretty close to pure Monte Carlo. We are slightly important sampled, although we're not really important samples, we're just biased, actually. We're not aiming towards anything particularly important. We're just biased towards certain directions arbitrarily because of our function that happens to generate things a little bit more strongly. So if you looked at how we were sampling the hemisphere right now, what you can imagine is, say you take a cube, right? And you make random points on the cube, and those random points are randomly distributed on the surface of the cube, okay? When you map that down to, because then we normalize those points down, when you shrink wrap that cube onto a dome, right, which we're then doing, what you're going to see is the lines, so this part of the shrink wrap, you're going to get a higher concentration of points as you approach these lines because they used to have more surface area and now they're being folded down onto that sphere. So out here, right, like right here where the sphere would touch, right, these places where the sphere would touch the cube, the density is correct. But as you approach these sort of corner areas where there was a larger surface area on the cube that got shrunk down onto the hemisphere, you get a higher concentration of points, right? So here, right here, can't see it, but here and here, right? Those points now have much higher concentrations than they should have. It's not horrible, but that is the case, right? So it's not really importance sampling, it's just biased, right? It's not, importance sampling is biased in a useful way. This is biased in an unuseful way. It's just biased. So it's bad, generally speaking, because it's sampling potentially a higher density of points in directions that we don't actually have any reason to believe will be beneficial, right? So ideally what we would do to improve this, if this was the main problem right now, it's not, but if this was the main problem right now, is we would want to change that bias towards being something useful, right? So rather than generating hemisphere samples that are biased the way they are now, or even uniform, we would instead generate hemisphere samples that were skewed towards the top, right? Shrunk this way. And that would be better for us, right? Okay. So as long as you understand that, again, that is not the problem we're having really right now. That's a very minor aspect of what problem we're having right now. It's just something to understand as we now talk about the problem we are having with sampling. All right. So the problem we're having with sampling right now is low sampling rate versus discontinuities in the function. This is the problem. And while it's nice to know what the problem is, unfortunately it's a hard problem to solve, but that's okay. At least we know what the problem is. So what does that mean? Well, what that means is lighting is something that has a really, really specific discontinuity in it always. And this is really what creates, I guess I would say, the entire problem of lighting, really, and why it's so hard to simulate, is probably, you could consider it this is the sort of the essence of it almost. Obviously, the fact that light along a ray is constant is maybe you could say the fundamental building block of the difficulty. Or maybe you could blame it on the fact that there's so many photons in the real world. But really, this part right here is the thing that's the most consternating, I think, when you try to develop algorithms to do lighting. And that is that when you are talking about lighting, if you were to look at the actual equations we're talking about, they're pretty nice and smooth, right? It's like, oh, I'm taking all this light in, and I typically have like a uniform concept of how that light is redistributed out or something. I've got these nice smooth lobe functions. As the light comes in, it radiates out. Even for specular surfaces, it's still kind of a nice smooth, still the functions tend to look like this sort of thing or even that sort of thing, whatever, right? It's not that bad. So why is it so hard to if it's so nice and smooth, why is it so hard to generate reasonable solutions? The reason is, of course, because of shadows. Shadows are the really big problem. And what happens with shadows is you get discontinuities in the light. This should have been a nice smooth integration of light coming in over a surface, but all of a sudden I put this block in the way. And now my function that would have been some nice thing, I'm just drawing, sort of representational graphs, that would have been some nice thing like this, all of a sudden now looks like this. Right? There's this big old huge discontinuous notch suddenly right in it, right? And so again, imagine back to the thing I was talking about of shooting, right? Imagine shooting along this thing. Well, now you just, instead of this nice smooth function that you could have imagined what it looks like just from a few sample points, because you just fit this nice curve through it and you'd be like, oh, that's the answer, right? Instead, you have to determine, oh, exactly how big is this notch? I don't know. I'd have to sample like really close and try to like narrow in on where it was to figure out how big of a notch was taken out, right? And so what ends up happening is when we say, what is the incoming light, rather than just any set of samples that happen to be like reasonably distributed across this thing, rather than that giving us a nice idea of what the light shape is that's coming in, we instead have this discontinuous notch taken out because of shadows, right? And worse yet, we could have multiple notches, okay? Those notches can be big, they can be small, but they are there, and there could be multiple of them. In fact, in a normal scene, there's lots of them. For any given surface, there's lots of notching, right? Now, it's worth noting that shadow in this case does not necessarily mean shadow in the sense that I can't see light, right? Take that out of it. What it really means is what surface do I see, right? So I've got something like this, or even let's say that maybe they're even the same place. Just two patches. This one's red, this one's blue, right? And here's my surface that's trying to figure out what it sees, right? If I look at the blue light that comes in over this solid angle, so I'm sweeping over this angle, I'm shooting out, right? Here's the red light that comes in, right? I'm like, this surface goes on for quite some time. So I'm like, as the cosine of the angle increases here, I'm just getting more and more and more and more red light. So it's just like, look at this nice thing that comes up, and then bam, it just ends right there, right? Not because the light stopped, but because a different color surface was in the way, right? So here I just have no blue, no blue, no blue, no blue, bam, instant blue, and then down with the cosine again, right? So it's just whatever surface I'm seeing, even if it's not shadow. It's just the fact that the things that are putting light in tend to be hard irregular, right? And they can be for any reason. It's two colors of paint on a surface. It's because there is a surface in the way. It just creates all these notches in the lighting. So what could have been a nice smooth function, because the actual surface sampling is nice and smooth a lot of times, becomes a really hard-edged function with lots of sort of notches in it, right? And so what we're looking at now is a function that has like this kind of nasty shape to it, right? Now you can't really do quite that, right? But it's like, it's things that look like this with all of these nasty little notches in them where it discontinuously changes. And so estimating this function becomes very difficult, right? Estimating this incoming light amount becomes very difficult. And so if we just do a few samples, even if they're uniform or random, no matter what we do with them, we're likely to not really get the same answer twice in a row. So let's say we've got 64 samples, right? And we're trying to sample this function, right? Well, this function is going to be this hemispherical function, right? So it's this, but in 2 dimensions over hemisphere. And as I'm shooting out, I'm finding all of these random values, like these values are just totally nuts, right? Some of them are super low, some of them are super high. So if I tend to sample a few more samples near the peak on one pass, I'm going to get a higher value. If I tend to have a few more samples that fall near troughs, I'm going to get a lower value. And this is what produces our flicker, right? Since we are undersampled versus the number of samples we need to take to really get the right answer, because we could take enough. In fact, here, let me show you what happens if we want to take enough, right? Here's our lighting, right? You can see that it's super flickery, right, as we go. And in fact, let me emphasize that since we're not using a continuous random value, we're using one that is the same every frame. When everything stops moving, our lighting sample stops flickering because we're using the same random sample, so they hit the same peaks and troughs, right? That's what's going on there. But if instead, for when we do our push lighting, we didn't do that, so here's where we do our compute lighting propagation, right? You see we have our random series. It's always initialized to 1, 2, 3, 4, right? It's the same seed every time, so we do the same samples every time. If instead our lighting solution was keeping a continuous random value, so let's say that we did this. Where is that? World mode. Lighting solution. So let's say we had this in here so it persisted, so our random series was changing every frame, like so. And so instead of series here, we just said like, oh, okay, it's actually solution arrow series, right? if we do this. So use it, and then we, at the end, we'll set it every time. Like so. So now we're keeping a random value that's going to go, that's going to keep going. Now we will get that flicker every frame, right? So this shows us what happens every time we recompute the lighting. We get a different result, and you can kind of see how that result is oscillating, right? Based on the fact that it gets very different answers depending on where it's shooting. And you can kind of see some regularity in this sort of thing, and you can see some of the obvious things that happen as a result. If you look at where these things are sampling, you can kind of see that, well, you know, if I look at areas that are not flickering much, right? So let's say I take a look back here in the black area. Why isn't that flickering? Well, it's not flickering because no matter where it casts, it never hits the light source. So there's no risk of flicker because it's never going to get an answer other than can't see the light source. Similarly, this has very high visibility to the light source, right? Because everywhere it looks is going to get light, more or less. It has very low flicker as well. On the contrary, people down here who could either hit the light source or hit the sky very easily, depending on how they're shooting, right, flicker quite a bit. People who are very unlikely to hit the light source don't flicker as much either, right, because they only hit it once or twice every frame. So they flicker at a very low flicker, right, whereas these flicker at a very bright flicker because they're going intense, and so on, right? And so you just get the biases in the function just become flicker. I shouldn't say biases. The undersampling, the fact that the thing is kind of notchy, we then get those sort of flickers in the function, right? In our poor estimation of what's going on. So what we can do is we can increase our sampling rate up to the point where we actually converge on the right answer because we're sending out enough points, right? And we can test that by just turning this back into a slow sample, right? So for example, if I go back to the where is that? In world mode, let's say I think we have a thing where we set, I don't know why we still have a debug light P in here. I don't want that. Well, I guess I do want that. Well, let's ignore that for now. Not what I was talking about. So if we want to go in here and just have a way of like switching it to slow lighting in the case where we don't want to output it every frame. So we can look here and we can see, okay, here's the lighting test with the output lighting textures thing. You know, if updating lighting or something like this, right? Then what we can do is this updating lighting flag is something that we could update periodically. So we'll just do here 3 updating lighting. Equals world mode updating lighting, right? And we can just put a bool in here. And we can toggle that on and off, right? So what we'll do is we'll say, all right, if you push certain keys, so let's say that you push F7, that'll turn updating lighting on for 1 frame, so we'll do 1 light update. If you do 8, it will set world mode updating lighting equal to not world mode updating lighting, so you can turn it on permanently, right? Maybe I want it to be 3 and 4. All right. So now if we look at it, we're not doing any lighting, right? Because nothing's happening. I can do a single lighting step if I want to by pressing the F3 key here, right? So that's 1 lighting step, right? There's another one. So I can recompute the lighting on a given frame if I want to. And then when I move the light source around, it won't recompute the lighting, right? But then I can compute it again. Does that make sense? Oops. And so then if I want to turn on permanent lighting, I can hit F4 and now I get permanent lighting, right? So now it's updating every frame. So now I'm free to go make a lighting thing that takes way too long to run in real time, which we had before, but then it turned out it ran so fast that we just started running it real time. But let's go ahead and go back to something that runs way too slowly. So let's say we set the ray count for sampling up ridiculously high. So we're just sampling tons and tons and tons. We have a much higher sampling rate than we had before, right? So now if I run a lighting sample, it takes a long time, right? Or, yeah, there you go. But our answer should be more stable. So if we look at what we get here, and I run it again, very little change, right? Did you see how little that flickered? It's very tiny amount of flicker, right? It's a very, very, very small amount of flicker. Make sense? Now compare and contrast that with the much less accurate version that we had before, where we were only sending out 64 samples, right? Now let's same exact position, same exact scene. Let's run it again. I mean, look at how much that lighting is changing, right? So again, the degree to which the light has kind of an uneven function coming in, the higher we sample it, the more we're going to capture the actual structure of the light, the less flicker we'll have. The less we sample it, the more likely we are to accidentally be sampling highs or lows, right? More than the opposite. And so the more we're going to end up with a flicker from frame to frame as we switch between sampling the highs more, sampling the lows more, et cetera, et cetera. So fundamentally speaking, that is what's going on here. And so what we need to address now is we need to figure out good ways of making it so that that flicker is not a problem for us, right? That's our goal. So how are we going to do that? All right. So one thing we can obviously do, if we want to, right, is we could go ahead and take this solution that we're using, and we could try to smooth it out over time, right? Because we know that the 4096 sample version, right, or an even more, we could do one that was even more than that, right? Arbitrarily high, right? Just keep cranking the numbers. We know that a version that samples things much more densely produces a much more consistent result from time to time, regardless of what the input series is. Yeah? So, what we could do is say over time, we'll just accumulate all the results we have so that the answer just keeps getting more accurate as we go, right? Furthermore, what we could do is say, well, since what we want to eliminate frame to frame is that flickering, then smoothing out over time is just going to naturally reduce it, even if we don't improve the solution at all in the process, right? So we kind of have a couple different ways we can think about having temporal elements there help us out with that flicker. So the question is for that, and I shouldn't say the question. The hard part about this, and we're going to face this no matter what we do, because we're going to want to, lighting's going to want to be smoothed over time, because it's never going to be solved perfectly, like I said. What we want to be able to do here is we want to be able to make it so that there's some way of corresponding surfaces from frame to frame. And this is pretty difficult to do, because it means that from one frame to the next, we would have to have a way of figuring out which lighting samples corresponded to which other lighting samples, right? And this is incredibly difficult to do. The fundamental problem is that if you look at a particular scene, it's very easy for us to do something like create lighting samples for every surface that we send down. It's much harder to figure out how those lighting samples should be used in how those lighting samples should correspond with the ones from the frame that came before it, unless you happen to magically know which ones they were, right? So we have to have some way of figuring out how those are going to persist. And I'm trying to think of the most efficient way to do this. Some elements of this could be pretty easy. Some elements could be pretty hard. I mean, I guess if I think it through, basically, here's what comes to mind, right? So I don't really want to have to worry about determining correspondence spatially, right? So there's spatial correspondence, and that's kind of like our voxel approach, right? Remember our voxel approach where we said, like, all right, let's divide the world up into a voxel, right? And we'll just say that, like, the light samples in this area you can sample from and find out what your sample probably is, right? We saw how many problems we had with that just because in general those voxel samples, you don't really know which surface they belong to, right? You don't really know, like, is this a surface that I should be counting or not? Is it one that would be in shadow relative to me or not? Like, it's not so good as ones where we say they're right on this surface of this thing. So we know which ones are on, like, this side of the surface versus this side of the surface for light sampling and so on. So spatial correspondence, I feel like, has a lot of downsides that I really don't want to be involved in, if possible. I'd like to avoid it. So I'd much rather have frame-to-frame correspondence of these things based more on knowledge of the fact that we drew the same thing twice. Not that it happens to look like it maybe is in the same place, roughly. If that makes sense. So, what I'd rather say is, like, oh, all right, let's say we have something more like, if I have an entity that's sending down a cube or something like this, right? Maybe that entity remembers its light index. So that if I send it down again the next frame, it just puts that same light index in there, right? And so this would be a nice clean scheme. The problem is, how do you know how to allocate light indexes at this point? Because if I want to do this, then I have to have something that remembers what light indexes are used on a particular frame so that things that are new for this frame don't use light indexes that are still being used by something in the frame, right? So if you imagine this is like an allocator at that point, where you effectively have some big block of lighting chunks. And what happens is you're like, oh, okay, somebody pushes down an entity that says it wants this lighting chunk, so it has to go there. And then someone pushes down an entity that says I want this one, so it has to go there. Then someone pushes down a new one, and you're like, okay, well, I guess I better put it here in some new space because I don't know which of these is going to be used yet, right? So you can kind of see why that's tricky. And you can see why that's tricky. Though there are some rather straightforward solutions to it that I'm just not sure how efficient they are. For example, one way you could do this was just when you push these things down to the renderer, you just tell the renderer, hey, here's the write back location for the light index. And it just doesn't allocate light samples to the new things until all the old ones have already been filled, and then it comes back, jumps back, and places those new ones in where they should go. So basically, you're talking about a second pass over the buffer, which is not a huge deal, you know? Um, and it kind of seems like that would be fine. So I don't know if it would be fine or not, but here's what that would look like. Let's suppose I took a look at the entity struct, right? And in here I basically said, like, okay, these things have an array of these sort of pieces that you can put in here. And those entity visible pieces need to have a lighting index that goes with them, right? Like so. That lighting index is something that the visible piece will track and report back, frame to frame, if it knows it. And I guess I don't necessarily know the part I'm having trouble thinking through is that the lighting index in a visible piece, right? You could just track that. And I think I can write the thing pretty straightforward that just makes it so that always comes through, so that you basically have frame-to-frame correspondence of the lighting just fine. The problem is, what happens when something then goes out of frame entirely? So an entity visible piece is now no longer being used, so it is like, it's not getting rendered anymore. It fell out of the camera region entirely, and it's just not getting rendered anymore. So that lighting index will now get reassigned to somebody else, as it should. But when this entity visible piece comes back in to view, it will have that same lighting index, right? So it will now accidentally pick up the lighting from something that is not correct, right? It's the totally wrong, wrong lighting index. Now, it's possible that just doesn't matter. The reason I say it's possible that it just doesn't matter is because we could just throw it out based on some kind of other piece of information. For example, let's suppose that we looked at the lighting index and said if the lighting indices are the same, we'll use it unless the position of this lighting sample that you're asking me to put here is actually not is too far away from the position that I last recorded for this thing, which would be correct in two ways. First of all, that would get rid of the problem that I'm talking about, but it would also get rid of the problem of the like entities that teleport, right? So let's say an entity hops onto a teleporter and teleports somewhere else. We would have to make special code to clear the lighting index. But if we were just comparing positions and go, it's too far away, the lighting would no longer be accurate, it would just set to recompute that one automatically, which is exactly what we would want. I don't know. It seems all right. Seems all right to me. I'm going to give it a shot. I'm going to give it a shot. Because if we can do the frame-to-frame correspondence this way, then we no longer have the problem of spatial correspondence, which just... Spatial correspondence tends to be really bad. You end up with a lot of visible glitches when you do spatial correspondence. In fact, you see this in games a lot nowadays. There's all kinds of weird things, like you look down at a puddle and you see the reflection kind of like trickle in, and then you move and it kind of smears, and it's like there's a lot of like temporal anti-aliasing stuff that you look at and it looks kind of bad. And I think most of the reason that looks bad is just because frame-to-frame correspondence that isn't tracked in some more intelligent way can be really bad. Although, you know, to be honest, that's probably just bad for other reasons. I shouldn't use that example because there's a lot of other reasons that would be bad. My feeling that why it's better to track frame-to-frame correspondence logically rather than positionally is just because I've seen how hard it is to do reconstruction filters for things like irradiance caches in non-real-time rendering systems, where you basically have like light information splats around the environment, and trying to figure out whether you can use a particular lighting sample or not tends to be a really hard problem that takes a lot of work to reconstruct properly. And there's pretty good ones now, but they are very expensive still. So the reconstruction itself is actually a pretty tough operation. So anyway, I think we do want to try this. So I'm gonna give it a shot. I'm gonna see how it goes. So what I'm gonna do here is say that when we do this when we send down these things that are gonna get lit, I'm gonna try to figure out a good way to sort of like actually line them up frame to frame, and we'll just see how that goes, right? So yeah, if you take a look at what happens here, excuse me, in push quad, what I want to do here in push quad is right now we've got sort of this light count, light index stuff getting set here as sort of an arbitrary thing, right? And what I'd like to do is I'd like to sort of upgrade this to being something where we are probably passing that down. So when we do a push quad here, instead of the emission being the only thing that's kind of set here, and honestly, the emission, I don't know that the emission is even something that we will be setting in push quad anymore, but you know, either way. In addition to the emission, I want to set here the light count and the light index as well. So in here, we're going to have a light count and a light index, and those will both be 0 by default. And the outer code will do something with that, right? So if we run the code now, what we'll get is no lighting at all. Like the game will just render the solid color of everything, because the whole point of this is that if you set the path that we did for non-lit is that you set them to 0 and you don't get lighting. So that's exactly what's happening here. So if I want to go ahead and put the lighting back in, then what I have to do is take anything that was going to participate in the lighting, such as one of the cube calls, which is, let's just do lighting on the cubes at first, right? So I want to do it on the cube call. The cube call would have to pass it down. So we should be able to emulate the same thing we were emulating before here by saying like, okay, you know, if the lighting is enabled or not, then we're going to go ahead and assign a light count to these things. Now we've got to draw all 6 faces of the cube. So we know that our light index has to be incremented by light count, but times 6, right? If that makes sense. And so then we're passing down light count, light index each time here. But the light index itself every time is going to have to increment. This one isn't really necessary. No, what? Push quad. It didn't like it. Is that because there's a second push quad here, isn't there? Yeah, that does the pack. Oops, those are backwards. I think. Are they backwards? How did I do those? Light count, light index. For some reason the count comes before the index. Don't ask me why. It just does. So now in theory this should restore lighting on the cubes, but only the cubes, because those are the only people who are having a light index passed down. So you can see sprites are non-lit. They just come through as their standard bitmap colors, modulated by whatever their actual sprite color is. But they get no lighting. And then the cubes get lighting. So if I were to run a lighting, right, all the cubes get lit, right? Like so. But the sprites remain unlit, which is exactly what we would expect. So that appears to be working properly. So next question is, well, okay, if the if push quad does that, then how do we now get the push cube function, which we're calling here? How do we get the push cube function to do something useful in terms of the light count, light index? And the answer is now we want to try and correspond these frame to frame. So we want to actually do an operation here that will allow us to try and do that. I'm going to make this so I can see these better. So this is push cube. And if we wanted to make it take an index here, a lighting index, that we then tracked, we would have to sort of say, like, okay, we need to know the location of the light index value that we're writing back. Because we're going to have to update this, right, in one way or another. So what we can do here is say, well, okay, if the thing in the light index store is a valid value that we can use, then we will use it. If not, we will assign a new light index to it and use that instead, right? That's basically what we're doing here. Yeah. Anyway, so this value right here would be the thing that goes into the entity's permanent storage. So when we are operating on this stuff and we do a push cube to push down the cube pieces, right? And I believe that's down here, right? So here's where we're doing a push cube, and the push cube, right, with all of this piece stuff that gets sent down. The push cube's emission value in this case is nothing. But the light index store is something, right? So we would say like, oh yeah, we're looking at the light index store piece light index, right? So we can send that down. Oops. Thought I added that. So now we would have a way of tracking this piece of information from frame to frame, because the renderer, when it assigns a light index to something, could write that light index back if it wanted to. And so that would be fine. So what we could do here is say like, okay, well, the light index store, if that's set to something, let's actually try to use it here. And if it's set to nothing, so if there's no pointer, then we're just going to assume that the lighting is not supposed to happen on this thing anyway, right? So this would also allow us another way to turn off lighting, I suppose, would be that we just pass zeros down for the light index. But you know, I can do that in a more sane way here by saying like, okay, right at the top, if lighting is not enabled, then the light index store is going to be 0, right? Then down here, I'll just look at the light index store and go from there. So if the light index store is valid, then what I'm going to say is like, okay, the total light count is going to be, you know, we're going to do exactly what we're doing here. We need 6 times the light count per surface to get what we actually need. And the light index is going to be assigned one way or the other. If the light index store value is not in range, and I guess in range is probably the wrong term here. I suppose what we actually mean is if we have 2 cases we have to handle. One is where we have an existing light index and it's valid. Another is we have an existing light index and it is not valid, right? The positions are too far. Those are 2 cases for the light index having an actual valid value, in addition to case 3, which is the one where we just don't have one at all, right? So we need to first check, all right, if there's a light index store pointer, then it's possible that the light index store pointer is pointing to something that is a light index versus one that's not. So if it's not pointing to something valid, right? So if it's pointing to 0, then we would assign it, I think. So we just say, look, it's whatever it is here, right? Otherwise, what we would do is use it here. So we'd say like, oh, okay. And I suppose these are the same. Right? And now I'm glossing over a big part here, which is this actually needs to be an allocator. So this is just wrong, arbitrarily wrong right now. So yeah, take that with a grain of salt. This is going to have to actually like defer and place this in an unused section of the lighting array, which is going to be the majority of the work that we have to do to get that to be a thing that works efficiently. But so here we've got our light index and our light index store, where we just say, okay, use whatever you used on the previous frame. That's it. Right. And so that should work relatively straightforward. Of course, we have the fact that we're only really doing U16s here. And off we go. And so now if I run this, in theory, I think this will still work. Because, well, I take it back. That definitely did not work. What did I do wrong? I was going to say it should just assign light indexes to all these things, and that should be it, right? Like, and then they're just going to use those light indexes going forwards. Unfortunately, that does not appear to have happened. Why does that not appear to have happened? So I guess the reason that's not happening is because the emissive light doesn't store anything. So that push light call that we do, I'm pretty sure this is the problem, right? This push light call that we do here, this one doesn't have a light index anywhere, right? So we would need to track that in order for it to work, because it's turning off lighting, including transmissive lighting. It's turning off all lighting calculations, period, for any light that that doesn't have an index, right? So for the time being, I don't really want to deal with that fact. We probably want to support just things that are only transient, because we have things like light sources that don't reflect light. Those we need to kind of improve our handling of eventually. So that'd probably be something we want to change in the future at some point. But for right now, it's probably fine. Oops. There we go. So now I think we will get our light in there, probably, hopefully, maybe. Yeah. Okay. So now you can see that we're running exactly the same way as we were, only now, in theory at least, we have stable lighting indices. We haven't done the work to actually make these work for real, because we need that allocator to work for things coming in and out of the lighting set. Right now, we don't have anything coming in and out of the lighting set because we're just looking at a tiny little scene. But remember, this is going to have tons of stuff all over the world that we're going to be moving through as we go. And so we need to have it understand how to take things in and out of the set, potentially. Now, we could also cheese that by saying, well, we don't really need to do that because we could just make it so that we hop from room to room. It resets the lighting or something like this. But, you know, just whatever we do, it has to be smarter than what we're doing now, which is nothing. Okay. So I would basically say that's all we really need to do for that. That's all we really need to do for making sure that our lighting equations are getting a slot that they can use to store things frame to frame. And so now what we could do really at the end of the stream here before we end, because I guess we've got about 25 minutes left, we could actually try to do a little bit of work with those to see if we can reduce the flicker, just as an example of what we could do. That probably isn't the final thing that we'll do, but something that's sort of similar to it's an example of what we could try to do, right? So what we would do here is we have to remember that the reason that our lighting resets every frame is because we are manually clearing it, right? We do an extract reflectors from quads call, and that extract reflectors from quads call is doing this emit clear here, right? So we have our points. They actually have an emission value coming in from the previous frame that we could choose not to clear, right? If this thing doesn't have any emission that's coming down, we could choose not to clear it, or we could choose to seed the C1 lighting with what was in the C0 lighting last time. I mean, we have a lot of ways we could try to sort of pull that lighting in from the previous frame, right? Let's see how we might do this here as an example. So when we do our accumulation steps, what you can see here is the dest emit C value, right, is getting assigned to the source emit C each time. So what we could do is just mix that in. This is going to be a really cheesy way to do this, I suppose. But we could just mix that in by saying, hey, don't clear the dest emit C1. Instead, just set it to whatever the dest emit C0 was from the previous frame. I don't really know what this is going to do. And you know what? We probably want to sort of reduce the contribution of that a little bit each frame or something like this. This is completely bogus. I'm literally just screwing around right now. Okay. That doesn't look like it did anything. So are we clearing these? Because that should have mixed in a value there. It doesn't appear to have done so. If I put in a mixing coefficient here for the, was it just that I wasn't doing that one as well? No, that's still. Let's see if I reduce the number. Yeah, that really doesn't seem to be holding much over per frame. Well, let's step in and find out why. Am I clearing these somewhere? I don't remember clearing them anywhere. When we do the transfer here, I don't think anyone ever clears them, right? Am I wrong about that? All right. Well, I'm going to go ahead and switch back to the debug compile. This way we'll be able to inspect the values easier. So here is the very slow running debug mode Flickr version. Right? Now what I can do is just step into that lighting and see what's going on there. I just want to take a glance at whether those values are being persisted or not, right? That's all I really want to see here. All right, here we go. And I'm going to hit the recompute lighting key. So we'll jump in here. And then we can see what our solution thinks it has in these right now for the various values, right? So yeah, let's take a look at emit C0 for this light index. What is the light index actually? Let's talk about that first. So this is light 1, which is what we would expect because this is the first time through the loop. And hey, there's some values in there, so that's good. And there's nothing in emit C1. So I guess I couldn't say why there would be nothing in emit C1. Because in theory, these should have been roughly the same unless it sent out all of its light. Maybe it sent out all of its light on that step or something, or... I mean, I guess it's possible. Let's just take a look at some other ones and see, is that a trend? It does look like there's never anything in C1. Oh, you know what? No, that does make perfect sense. there shouldn't be ever anything in C1 because it's cleared even on the last one. We don't discriminate in this loop between whether it's the last loop or not. So C1 actually does always get cleared at the end of it. So that's actually not surprising at all. I take that back. Okay, so that's fine. But we are getting actual light values coming in here under emit C0, right? So we should be able to mix those values in. Let's see if we can do a better job of it. So I think the problem that we're going to have here is if it's just that much flicker is introduced every frame, the problem is this is not going to cut it. Just starting with existing values isn't going to cut it, right? Also, I realize this doesn't have to happen since we clear it at the end of every frame anyway, right? It's really only this one that has to get cleared in that way. So what we would have to do here is we'd have to save into temporary buffers what those values are so that we could mix them at the end or something similar to this, right? We can't use our scratch buffers for it. So what we would have to do is say, okay, temporarily, and this is not a smart way to do this, but, we can, again, we'll optimize this and do more of a ping pong buffer thing for it if this turned out to be what we were going to do permanently. Yeah. What I want to do here is just say, okay, let's keep those around and then we'll mix them at the end so we can be sure that we're taking the final solution of the first one and adding it to the final solution of the second one. So that we have two full solves and we can control the blend rate rather than taking the solution and including it in the distribution step, because that will just probably add all the noise right back in, right? So let me go ahead and do that. So in here, what I want to do is something like last emit and last direction. Why is that? Why didn't that breakpoint set? Not that I need it to set. And then what I want to do is when I start, I want to save into there whatever those were, right? So what I'll do here is say last is valid. I'll come into the render group. The first time through, obviously, it's not valid. So we'll deal with that in a second. But my last emit, I'm going to take here before I overwrite. In fact, you know what? I don't even need to do this. Let's just copy it. Do I have a copy struct? I guess I don't. So I'm going to take last emit here, or I should say I'll take emit C0, and I'm going to copy it oops, that's not what I wanted either. I wanted average light direction. So what I want to do here is just copy these two arrays. Again, this is not good. But that's okay, because we're just doing this for testing purposes anyway. So we're going to do that copy there. Don't ask me how that got inserted. Probably was trying to hit the buffer switch key or something like that. Anyway, right in this code base, size of is not capitalized. There we go. So that will give us a copy, and then we can do our mixability, our mixing of those at the very end. So in here, where we do the final sort of averaging of the points and all that stuff, this is where we could do our mix. So we could do mix emit C0, which is what we're going to use. We can say emit C0 point index equals, a lerp, let's say, between the value that we were last time and the value that we computed now. So we have our last emit. We have our new emit, and we can go some amount of the way there. So let's say we go a quarter of the way there, so 4 frames. It takes 4 frames to change the lighting completely, right? Just making up a value here, and in fact, we can just do it like this. And so the same will be true for the normal here, right? We can say, all right, the solution, last direction, will lerp towards the new light direction as well, and off we go. So now we should have 4 frames of lag on our lighting, I think. And that does look exactly like what happened. And since we don't want to do this in the case of, I want to do a if solution last emit, last is valid. If this last, if we have never taken a light sample before, then I don't want to do that, right? Like if we've never previously had any light, then I don't want to blend it in. I don't want to blend in zeros because that'll just cause our lighting to fade in for no reason. If we want our lighting to fade in, great. We can fade in our light sources. I don't want to have the lighting solution enforce a fade here. So what I want to do is just, again, do the opposite copy. So say like, oh, okay. In fact, I don't even need to do a copy. I could just do it like this. I could say last emit equals solution last emit. Last direction equals solution last direction. And then if we don't have a valid lighting solution, then what I can do is say, oh, last emit will actually just be this emit. So it'll just lerp between the value and itself, right? Which will do nothing. So that will prevent us from having that fade in. So now when I run it and I do F3, I should get, okay, that didn't work at all. So I don't know why. Because I'm not using those. There we go. You gotta actually use the variables you make if you want them to work. Pro tip. There we go. Oh, no, that's still... Why are we getting... That's weird. I don't know what to make of that. That was very strange. Did you see that? It was like we weren't getting any lighting on our walls all of a sudden. I must have introduced a little bit of a bug when I was doing the last emission stuff. Well, you know what? So we don't really know that that's true because we don't know that these are getting completely... Well, we do. We think they're completely stably assigned. We'll have to see. We can debug it later. All right, let me... So in theory now we're blending across multiple frames, and it does look like that, right? We still get some flicker. The flicker is definitely less. We could try reducing that value and see what happens. Here's one that takes 10 frames. Right? Here's one that takes 20 frames. And here's one that takes 100 frames. You know, hopefully what you can see here is we can definitely combat that flicker by just having lag in the lighting. We've done nothing. We don't even have this accelerated, so we're not even taking very many samples compared to what we could be taking. And that's usable, right? I mean, that's a shippable lighting scheme, sort of, in terms of just the you know, the degree of, like, disruption of the game experience. It's very little, right? So let's say we wanted this to be something like 20 frames or even just 10 frames. I wonder what we would have to set the sampling rate up to. And of course, we could do better with our sampling anyway than we're doing now. But let's say I doubled the sample rate there. Yeah, so I mean, honestly, I think this is going to work just fine. Because we're going to get a lot more samples. So I think we'll be able to crank it down pretty low. And what we now know is that if we're willing to take, let's say, I wonder if 50 frames is sufficient. Something is weird about my lighting startup. It's not actually obeying that last is valid. And I don't know why. What am I did something stupid here. What did I do wrong? I want to go step into that. Hold on one second. Is this value not cleared or something? Because I thought they were all cleared, but maybe they're not cleared. It could be that that value is not cleared at startup. I should just go check. Okay, turning the lighting on now. So that's setting it, right? And lasted valid is now 1. So this lerp should always be just two things that are the same value, right? Okay. That's going to get optimized out, I'm sure. That's weird. So what did I do wrong there? Because that should have just worked. And those are both the same value, so lerping between them should have just been a straight copy. But something about the startup is busted, right? You saw that, right? It's as if it's not doing that. But then once it's done, it's correct. Like, now it's fine. So something about the startup there is kind of busted, and I don't know why, because the only two values were persisting. The only two values we're persisting were, you know, we're just using pointers to the same. Ah, but average direction to lights version won't be normalized. So it's not quite right. Yeah, so technically you would have to do that, or rather, that would be the smarter thing to do anyway. So the emission value is probably fine, but the average direction is not. Hey, look, that fixed it. So what happens? What would happen if we actually put back in our little weird snake dude? This will be the last thing I'll do today. I'm just curious what would happen if we added that weird snake dude back in with the light on him. So we still have some kind of weird bugs going on there. Like those lights only seem to work in certain places, but as they go up, they don't. I wonder if we've got some like light assignment problems there. And you can see the frames of lag are worse when you have a fast moving entity, right? So this is why we want to reduce the number of frames of lag there. So we can capture faster moving entities. But look at how there's no light happening up there. So that's a bug, but I'm not sure what that bug is. So we definitely have a light index assignment bug that we need to debug. So that'd be our thing to do for next time, right? All right, let's do a brief Q&A. And since we might not do a Handmade Hero next week since it's holiday break, I need to make a note to myself. Because we're going to need that. Because yeah, I'm pretty sure that we just have some kind of lighting index assign like that. That was a pretty hacky thing. I just kind of did it quickly and so we could test with it. But when we go finish that lighting index assignment, I'm feeling pretty good about that. I think we're almost there with lighting. If we don't have any questions, we can end early. Taradub. Yesterday, someone asked if it will be beneficial to have more test scenes for lighting tests, and this was never answered. Yeah, that does sound like a good idea to me. Arif, don't you use the to-do.txt in the code direct to make notes? Yeah, but we never use it. So I wanted to put it right in the code so I can't miss it. Long Boolean, what is your take on the use of machine learning to approach one of these? I don't have an opinion yet because I've never tried it. Probably it's not as good as people probably say it is, but it's also probably going to get better. So I suspect that like over time we'll find that machine learning can generate algorithms for us that we want to use, and you know they will get better. All right, I have to go, so I'm gonna do. So we don't have a flood of questions that are on this topic. I'm gonna go ahead and wrap up early. I apologize. All right. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you want to follow along with the series at home, you can always pre-order the game, and it comes with a source code updated nightly, so you can play around with it yourself. We also have a forum site you can go to if you want to ask questions, a page you can go to if you want to contribute to the things like the episode guide and stuff like that, a schedule about that tells you when we'll be live, and the aforementioned episode guide, which has like all of the old episodes annotated. It's pretty awesome. You should check it out. That's it for this week. There probably won't be a show next weekend because of holiday break, but we'll be back sometime after that to finish the lighting off. It's coming along pretty nicely. I'm pretty happy with it, actually. So hopefully you'll come back and join us in 2 weeks for that. Until then, have fun programming. Have a good holiday season. And I'll see everyone on the internet. Take it easy, everybody.